Good afternoon. On the off chance that the weather clears up, there's going to be a rocket launch from Virginia that should be visible from here in the southwest sky at 7:40, more or less. Yeah. So just after sunset. Could be fun. Any questions on lingering questions on Lab 3? Or questions on Lab 4? I got a bunch of questions on Friday, so I thought I'd try and put together Lab 4 into one big spanning picture on the board all at once. And but before I do that, I want to say that Sean Carroll, who was a student last year, figured out how to hook a microchip port expander to the CPU. It is yet another SPI device, but it also looks like a 16-bit parallel port. Actually, it looks like two 8-bit parallel ports. And each of the 8-bit parallel ports can be set up as input or output with pull-up resistors, just like any other microcontroller port. So it gives you an extra 16 I/O lines for the cost of 3 pins on the microcontroller. And he's documented how to set it up and given a little example that uses push buttons or switches and LEDs. So you might want to take a look at that. If you think in your final project you're going to need a bunch of I/O lines, you may want to look at the port expander code, which is zipped up on the home page, a 4760 home page, in the student written section. And he's still playing with this and developing it. This is part of the approach we're doing, which is to decide what should be on the board we make everybody build next semester. So Lab 1 next year may be build the board you're going to use. And we think what should be on there is, of course, CPU, a crystal for precision timing, port expander, maybe the DAC, maybe not, probably a plug for a TFT display, but your suggestions are welcome at any time. What should be on the minimum board that would be useful in this class? Again, any questions about Lab 4? So I got some questions on Friday. Oh, by the way, there's 2 cables that you can use for serial connection to the PC, for the console connection. You're going to use just one of them. You don't need to use both. We're using both. Choose one. I don't have enough for much more than one per group, so that if you leave yours someplace, you get to buy one. Well, what I thought I'd do then is to talk about, if there's no questions, talk about the whole thing as one big process. And so in the center of this, of course, is going to be the PIC 32. But within that, we're going to break down some sections. First of all, there's going to be a motor with the fan blade attached. And what I've strongly suggested in lecture that people do, but they're not doing it because I said it differently in the lab, is to put the infrared emitter on one side of the blade and the infrared transistor on the other side of the blade, so that you're looking through the fan, not at the fan. The signal noise ratio is much, much better. So output of the infrared transistor is going to be a amplifier comparator. And then that's going to feed into the one of the input captures, which of course is hardware, which is going to be run by a timer, which is also hardware. And as a reminder, the code in Lab 1, which I'll show in just a minute, is exactly what you're going to use here. But before I go there, are there any questions about this circuit? This is the input comparator circuit. You notice that the positives are noted by stars, which refer to the bottom of the image here. Long lead is on the emitter, and the phototransistor are as marked. You're going to have to adjust this threshold so that you get a reliable square wave out of here. And an interesting thing about this square wave is that it is pulse frequency modulated, not pulse width modulated. So if the motor is running at a low speed, you get a waveform that might look like this, and if it's running at a high speed, you'll get a waveform with the same duty cycle but a higher frequency. But the average duty cycle will be the same as the low speed. Therefore, you cannot connect this directly to the output compare that you're going to have to run through a low pass filter to the scope. So let's say scope channel 1. And we're going to want to set this, so this is again hardware. It's going to be run off of yet another timer. And the time constant of this should be something like 0.1 second or so. Maybe a little shorter than that. It's not very critical. I would say this resistor ought to be in the region of 10K ohms or so. But we're going to have to do a translation here. So you're going to have to then build some sort of software that's going to take the input capture, convert it to a frequency, format that as a PWM signal, and output that to the output compare. Also, you're going to have to feed the frequency to your algorithm, which is going to compute C of t. You remember C of t from the last lecture. Any questions on that so far? So let's go look at that input capture code from Lab 1, digital capacitance meter. Way back in the old days, there's a timer capture signal generator with 1.1, and if you will remember, there was an input capture interrupt service routine, which you had to modify in Lab 1 because you needed a time, not a period. And in this case, you're going to want the period between, say, positive edges of the motor rotation or of the blade passing. So you're going to want to do precisely this in the interrupt service routine. of course, this has to be run by a timer. And that brings up another interesting aspect, and that is if you run one of these timers at full speed, 40 megahertz, how many milliseconds does it take to overflow? Who's done the calculation? It's a nice thing to keep in mind just in general. It's going to overflow in 60,000 counts, más o menos. So 1.5 milliseconds, right? What's the maximum speed of your motor? Anybody? How much?
3,000.
It's about 3,000, yeah, which corresponds to 50 revolutions per second. So that sounds like about 20 milliseconds between revolutions. Divide that by 7, and we get about 3 milliseconds between blade crossings across these infrared detectors, which means you can't possibly run the timer at full speed. You must use a larger prescaler than 1. It won't work to use 1. So what seems like a good one to use? Same rules have to apply that you applied in Lab 1. You want the fastest time that you have to time to have at least 100 counts, and the slowest time can't overflow. The longest time can't overflow. What's the longest time you have to worry about? Well, gosh, if the motor's going 0, it's a really long time, like infinite. But let's bound it on the bottom. I think I said we're not going to test you any place below 500 RPM. So to give it a little headroom on the bottom, bottom room, give it a little bottom room, I guess you'd want to set the maximum length of time that you need to measure to maybe 10 milliseconds, which would be 100. No, I'm sorry. 100 RPM. 100 RPM divided by 60 is about almost just a little under a second. 0.6 seconds is the longest time you might have to measure. Oh, divided by 7. 0.1 seconds. So around 0.1 seconds. So you're going to have to measure, you're going to have to be able to measure in the range of 0.1 second to 0.01 second or so. So you're going to have to figure out the prescaler that you have to use on this timer to give you enough dynamic range of the appropriate frequency to actually measure the blade crossing times. So I said long ago, weeks ago, this code is still okay even if the timer overflows once, because subtraction works across an overflow. 2's complement subtraction works across an overflow as long as the capture are all shorts. If you make them ints, it won't work. Yes?
Could we use a 32-bit timer?
You could use a 32-bit timer. Yes, you could concatenate timers 2 and 3 and make a 32-bit timer and have a tremendous dynamic range. Then you have to worry slightly, can you run the output captures from 4 and 5? 5 is in use by threads, PT threads, so you're left with timers 1 and 4. I don't know, will timer 4 run the output compares? I don't know either. One of the many bits I haven't tried on the architecture. Let's say you're running this control loop and you shuffle your rear end in the chair and then touch the circuit and you generate a noise spike in the middle of the pulse cycle, and you generate a bogus interval. And suddenly your motor decelerates. How are you going to make the system noise resistant to impulse noise? Any ideas? How do you get rid of impulse noise in general in a signal? Median filter. Ignore outliers. Now, in the case of the motor, you have a really good idea of what the RPM limits are. And if you get an RPM reading which is outside the limits that you know the motor can do, you better throw it away. So if you suddenly find that the motor's going 10,000 RPM, check, make sure it's not smoking, and then try and figure out what's wrong with the algorithm, because something's wrong. So you're going to have to get rid of narrow pulses, probably by doing consistency checks for minimum and maximum reasonable motor speed, and you might want to look for outliers. The last three readings were all plus or minus 1% from 50 milliseconds, and this one is 10 milliseconds. Throw it away. So this signal coming out here, you're probably going to want to scale so that (3,000) RPM maps into 3 volts. Or something like that. How do you do that? Well, it turns out that probably the best way of saying this is that 3,000 RPM maps into the timer interval. So you're going to set this timer to some interval. You're going to set this timer to some interval, which is going to be your full scale reading. So let's say you set the timer. Now the output compares, by the way, are going to generate a PWM, which you need for the motor. And the motor PWM has to be at around 1 kilohertz or less. So at full speed, timer, divide by 1 prescaler, the timer interval for 1 millisecond is, of course, 40,000 counts. So that says that you should map 3,000 RPM to 40,000 counts on this signal coming into the output compare unit. Where do we set output compare? Well, let's go back to the proto-threads page. Look down here on output compare units. The output compare unit example sets up one output compare unit as a PWM unit. So output compare 3 here is set up as a PWM unit, and we set the PWM value by setting this strange macro DCOC3 PWM on time, which now has to be in the range. If we're going to have a timer interval of 40,000, then the PWM value has to be in the range of 0 to 40,000. That being the time between the repetition of the PWM signal. So that's how I would probably scale 3,000 RPM to make it 40,000 after it's been scaled. Now C of T requires another input, which is from the USART by way of PT threads. So threads is going to be running out here. The PT input, which is connected by a DMA channel here. So you're gonna have a USB to serial adapter here feeding the USART. The USART is going to DMA burst over to the PT input. That's going to give you the desired RPM, the desired speed. We're going to get RPM from here also, the actual RPM. This is the desired RPM. Now we have enough to compute the error, which is the basic input to C of T. And to summarize from last Friday's lecture, then the output PWM, oh, we need another PWM channel. Ah, yes, another PWM channel. Output compare, PWM. Which is going to feed through a low-pass filter to scope channel 2, but the unlow-pass version is going to go through the opto and back to the motor. There is a galvanic boundary across here. Everything on this side, everything, the motor and this side of the opto, has a separate ground and no other electrical connection to the microcontroller. Well, let's write the output PWM signal. Is going to be conditionally 0 if C of T is less than or equal to 0. It is going to be the timer period if C of T is greater than or equal to the timer period. So that if you ever produce a value from whatever arithmetic you're doing here, you're going to be multiplying some RPM, 1,000, times some proportional constant, 1,000. If the product ever gets bigger than the timer period, you have to saturate it at the timer period. If you allow it to wrap, then as your command goes up, your speed will go down. You can't allow that output to wrap around. It has to saturate at 40,000 or whatever your timer period is. And if neither of those is true, then you're going to have a scaled version of C of T, which is going to be equal to P times the error at time n plus D times the error at time n minus the error at time n minus 1 over dt. This is what we talked about last time. plus the max of I max and I times the sum over I from I equals last zero crossing of the error, that is, to n dt. If you have a constant speed servo loop, if you're calculating C of t at constant dt, then you can multiply d times 1 over dt and I times dt and save a whole multiplier or divide on every cycle. And so you have to decide, are you going to update at a constant rate, let's say 100 times a second, or are you going to update every time there's a blade crossing and therefore new data on the control channel, new data on the RPM channel? If you do that, then dt is going to be different for each different speed, and therefore you must explicitly do the divide and the multiply. So how big should P be? So it depends. The absolute magnitudes depend a little bit on how you're scaling and the units you're using. Are you going to use RPM or RPS? Everybody in the group should agree on that. It doesn't matter, but you better agree on that because you don't want to crash your lander into Mars, which is what was done a few years ago when half of the engineering team on the Mars lander used MKS units and the other half used imperial units. And so half the calculations were done in Newton meters and half were done in some ungodly foot-pounds or something. So you have a bunch of decisions to make here about representation. Doesn't matter what you use, except the magnitude of P is going to change. But in any case, if the system starts saturating at 40,000, oh, by the way, what's going to give you, let's say you're sitting at low RPM. And so you're sitting at 500 RPM and you command 1,000 RPM as you're going to be asked to do. The fastest way to get from 500 to 1,000 RPM is to give the motor full power. Boom. So in that case, you're probably going to want to scale P times the error to be something like 40,000, which will be maximum power, assuming that you have the time interval set to 40,000 here. So the motor is both the input and the output, because it's a closed loop system. We have an infrared sensor that's feeding frequency data in, RPM. We have to convert that to a numerical frequency so we can output it by using the PWM channel, one PWM channel. We need to use the RPM number and the desired RPM to calculate an error. Then use the output of C of t to run the other PWM channel And there's no particular reason why they have to use the same timer, although it seems like a reasonable idea. A low-pass version goes to the scope. A raw pulse version goes to the opto. These two channels should be the first thing you build, not the last thing. Because you're going to need these two channels to debug the control system. If all you're doing is actually, you get pretty good at it. If you listen to the motor long enough, you can tell the RPM by listening to the tone. Sadly. And you can actually tune this pretty well by listening to the tone of the motor. But probably it's going to be more cost effective, unless you have pretty good pitch, to just build these two circuits right off, get the output compares running, get the C of T output. This will tell you if there's a numerical error. Get the frequency output converted from frequency code to pulse width modulation code, so you can make sure that the sensor is working correctly and reliably. Set that up first. Given that you're going to run the control loop about 100 times a second, do you see any particular reason not to use floating point? I don't. So if you want to do all of the calculations in floating point, you can, because you have enough time. In this case, the control loop is limited not by how fast you can update the numbers, but by the blade crossing time. And so floating point calculations here have no particular penalty. You could do them all fixed point too, that would work also. Any questions? You want to adjust these time constants. Both of these should have a time constant of around 0.05 to 0.1 or so. You want the time constant here to be much longer than the PWM time, and shorter, and much shorter than the motor response time. And so 0.05 to 0.1 seconds fits both of those constraints. Have I left out anything? Oh yes. The reset, like any integral, this has to have an initial condition. And the initial condition on this should be to reset it to 0.9 of last value at zero crossing. So you're going to reset the integral when the error crosses zero. So if you've just commanded zero, if you've commanded 1,000 RPM, if you command zero, the motor stops. If you command 1,000 RPM and the speed changes like this, then you're going to reset the integrator here where the error is zero. You're going to reset it here. You're going to reset it then every time it crosses zero. And you're going to reset it to 0.9 of the last value it had. Clearly, at the first zero crossing, you're going to reset it back to zero, because that's the last value it had. But never mind. Because it's iterative. After a few oscillations, it'll converge on a reasonable value. So that's kind of the big picture. This stuff is software, threads, C of T calculation, frequency calculation. The rest of it's parallel executing, so to speak, hardware. The timers, the input capture, the output capture, the input capture, the output compare are all hardware modules that you're going to program up to handle I/O for you. Does the scaling make sense? This tends to be one of those things that you say nod and say yes, and then when you actually code it, it doesn't make sense anymore. So after you've tried to code it, come back with questions. But why does this condition have to be true? What physically in the system requires that that be true? That the output is 0 if CFT is less than or equal to 0. What physically matters here? Oh, I modified the motor driving stuff, by the way, so that the references are now to the 2SK4017 instead of the Buzz 73 because I don't have any more of those. But what physically about this circuit means that a negative value doesn't make any sense? Yes? Well, right. With the diode there, if you reverse the current, you'd have a short circuit across the motor. So that surely is true, right?
You can't drive the motor backwards.
You cannot drive the motor backwards because there's only a positive source of current. You can drop the current to 0, but you can't make it negative through that motor. And in fact, these are not brushed motors. They do not run backwards. If you reverse them across the power supply, they go bang and stop being motors. Rather quickly. And I tested one of these things because I wanted to see what would happen. I hooked it up backwards across one of the power supplies and slowly turned up the voltage from 0. And when I got to 1 volt, the current through the motor was negative ½ an amp. And when I got to 2 volts, it blew up the motor. So the motors are short circuits if you reverse the power on them. So for a number of physical reasons, you cannot produce a negative output here. So you have to clamp it at 0. You have to clamp it at the timer period because if you don't, if CFT gets bigger than the timer period, then you'll wrap to a small number and you'll be commanding the motor to go slower rather than faster. As a guess, I think that you're going to want to set P to be significant, D to be insignificant, and I to be fairly small but significant. How big should the proportional term be? It depends on the units you use. If you use 3000 RP, if you're using RPM, 10. If you use an RPS, 100. Anybody got to run a closed loop yet? I've seen some people running motors and getting signals out of the comparators, but that's about as far as I've seen anybody get so far. Nothing on this side of the opto connects to the microcontroller at all. No ground, no nothing. What's the value of that resistor? Yes, you have to read the write up to know what the value should be. It's in the paragraph above. It's amazing how many people don't read the lab. Just look at the pictures. You need to know the size of that resistor. You need to know the size of that capacitor. It varies. That's why I didn't put it on the schematic. But it's in the text. Oh, you're going to need to have some sort of command language at the console that allows you to set parameters. And I suggest something like this, which is easy to parse. Set the speed to 300. Let's make it RPM to make it simple. Set the proportional, the integral, and the differential term. You're going to want to have floating input. So you're going to want to use, you want to be able to probably do all floats on the calculations. Do floating input. I would not build an interface where you have to change all 4 parameters every time you change one, because the TA is going to make you change stuff back and forth and all over the place. And so if you make it a bulky user interface or a hard to modify user interface, you're going to do a lot of typing while you're checking out. Any more questions? Any questions? Real quiet group. Did I say everything I wanted to say? So what's the first thing you're going to test? What's the first thing you're going to test? Time's wasting. There's only a week left.
We tested the motor
with the infrared and comparator over here. So the natural next step would be to get the input capture running then, and then the channel output to the scope, and that'd be relatively little code. Probably lines of code, right? I would say when you get to it, make CFT pretty simple to start with, like use RPM times a constant as the output. Just get it running. Get something running. Oh, yes, reminds me. Do you want the motor to run at when the system starts up, or do you want it to be at 0 RPM? Do you want to have to command it to run, or should it be running? You're going to have to make a policy decision on that and set the PWM in main before you start a thread to enforce the initial condition. So you could set the PWM output in main to some non-zero value, and the motor should start up. That could be a way to test the motor with absolutely no control code. So 1 week from tomorrow, the first groups will be starting their final project. Right, this week. Oh no, or this is the first, wait a minute, this is the first week of the lab, isn't it? Oh, that's right. No, that's right. No, 1 week from tomorrow. Because the first lab is tomorrow night. 1 week from tomorrow night is the second lab, and the next day you start final project. So, 1 week from now, you're going to have to hit the ground running figuring out your final project. So if you're going to need to order parts, you need to start now, or you're going to, or possibly wait till I order parts. The first time will be not next week, but the week after that, which is the 24th plus 7 would be the 1st of November, maybe. So, or maybe the 31st. So, when you order parts, if you ask me to order parts, first of all, the aggregate of all the parts you buy, that I buy for you, has got to be less than $20. And what I want from you is a part number in the text. I don't want an Excel spreadsheet. I don't want formatted text. I want a vendor and a part number and a quantity. Typically, I have to do 10 or 15 or 20 of these in the morning. I don't want to think too much. So if I paste the part number into the database on DigiKey and it doesn't work, I just delete it. I don't search, I don't write you email, I just delete it. So give me unformatted text messages, vendor, part number, quantity. And it has to be one of the vendors that I specified in the list. And I will order it probably with 3-day delivery, 2 or 3 day delivery. So Monday orders would be here typically by Wednesday or Thursday. Yes.
Repeat what you said about the cost.
The aggregate cost of everything you order through me has to be $20 or less. So you can spend up to $100, but I can only afford to spend something like $1,000 on parts for each individual project that are not amortized at all. They're gone, right? I give them away, they're gone. And the department won't let me do much more than that. They don't even like that too much.
When will we receive feedback on our project proposal?
Hopefully by lab this week. Anything else? Okay, lab was open this morning. Lab will be open tomorrow morning, I believe. I said, let's just go look at the schedule. Yeah, 9 to 1 tomorrow. So stop by and work on Lab 4 or talk about the final project. See you in lab.